Hey there, and welcome. You ever just stop and really look at the stuff around you? A window, a bottle, the phone in your hand. We use them every single day, but how they're actually made is this kind of hidden magic. Well, today, we're going to pull back that curtain and dive into the incredible engineering story behind how things get made. So let's just start with a quick question to get the wheels turning. Picture a simple glass bottle, for water or whatever. Now, picture the super high-tech screen on your smartphone. On the surface, they seem like they're from completely different planets, right? But what's the real connection between them?
And here it is. They are both these amazing triumphs of what I like to call invisible engineering. They show how we can take really simple, basic raw materials from the Earth and, through some serious ingenuity, turn them into things with incredible precision, usefulness, and even strength. That whole transformation, that's what we're talking about today.
Okay, so let's dive right into our first case study, the forging of glass. This is just the perfect example of taking something like grains of sand and transforming it with fire into something crystal clear and amazingly strong. The actual recipe for glass it's surprisingly simple. It all starts with silica, which is really just a fancy word for high purity sand. Now, the big problem is that sand has a crazy high melting point, so to fix that, you add soda ash. It acts as a flux, which basically just lowers that melting point and makes the whole process way more energy efficient. And then you've got limestone, which is the stabilizer. That's what gives the glass its strength and, this is a big one, keeps it from dissolving in water. But the fourth ingredient, cullet, is kind of the secret weapon in modern glassmaking. It's really just crushed up recycled glass, but it is a critical part of the mix. See, because it's already been glass once, it melts at a much lower temperature than all the other raw materials. That means it dramatically cuts down on the energy the furnace needs, which is fantastic for the environment and, for the company's energy bill. The whole process really boils down to these four main stages. First, you've got batching, which is just precisely mixing all those ingredients we talked about. Next up is melting, where it all gets zapped in a giant furnace. Then comes forming, where the liquid goo gets its shape. And finally, you have the super important finishing step, which is what actually makes the glass strong. So let's zoom in on a couple of these.
To really get a sense of the melting stage, you have to appreciate the raw power we're dealing with. We're talking about temperatures around 1,500 degrees Celsius. That's 2,700 degrees Fahrenheit. It's so hot, it literally turns solid grains of sand into this glowing liquid that looks just like lava. It is a truly elemental transformation.
Now, once you have that molten glass, this is where the engineering gets really clever, because it can go down two totally different paths. If you want flat glass for something like a window, you use the float process. A ribbon of molten glass literally floats on top of a bath of liquid tin, and gravity just naturally pulls it perfectly flat. It's genius! But for containers, like bottles, you use the press and blow method. A gob of glass is first pressed, then inflated with air like a balloon inside a mold. Just two different problems, two completely brilliant solutions. What's so wild is that making glass isn't just about intense heat. It's also about the very careful, controlled removal of heat. If you just let a new piece of glass cool down on its own, the internal stress would make it shatter into a million pieces. So to prevent that, it goes through a process called annealing. It's basically a long oven, called a lure, that cools the glass down super slowly. This relieves all those stresses and is what gives the final product its stability and strength. Okay, so we're going to shift gears now. Let's go from the brute force of a furnace to a world of almost unimaginable microscopic precision. This second manufacturing idea is what we can call the art of layering, and you can't find a better example than the touchscreen on your phone. See, a touchscreen isn't just one thing. It's more like a really, really carefully assembled sandwich. You've got the tough cover glass on top that you touch, and the display on the bottom that shows the image. But all the magic, that happens in between. You've got a sensor layer, which is this invisible grid, a controller chip that's the brains of the operation, and special optically clear glue holding it all together so you can see through it perfectly. So how do they make that invisible sensor grid? Well, it's done with this incredible process called photolithography. Think of it like developing a photograph, but on glass. You start with glass that has this special transparent conductive coating. Then you cover that with a light-sensitive film. After that, you shine UV light through a template or a mask, which hardens the film into that grid pattern you need. Then you just wash away the unhardened parts, and finally, an acid bath eats away the coating that isn't protected, leaving behind a perfectly transparent, microscopic grid of sensors. Amazing. All right, on to our third big idea, And this one is all about deconstruction and reconstruction. So instead of melting or layering, what if you took a natural material, like wood, completely broke it down into its most basic parts, and then rebuilt it into something totally new? Well, that's papermaking.
So that deconstruction part, that happens when you turn wood chips into pulp. With chemical pulping, you basically cook the wood chips in a chemical soup that dissolves the natural glue. It's called lignin that holds the fibers together. This gives you really strong paper, like for grocery bags. On the other hand, mechanical pulping just physically grinds the wood up, which leaves the lignin in. And by the way, that's why old newspapers turn yellow. It's that leftover lignin reacting with light.
Now, get this. This fact is just incredible. The pulp slurry that gets fed into a paper machine, it's over 99% water. Less than 1% is actually fiber. So when you think about it, the entire challenge of making paper is just a massive, high-speed, dewatering job.
And the machine that solves that problem is the gigantic Fourdrinier machine. First, that watery slurry gets sprayed onto a moving mesh screen, and a ton of water just drains out immediately. Then the super fragile sheet of, well, mush gets squeezed between huge rollers. Finally, it snakes its way through hundreds of feet of steam-heated cylinders that evaporate all the remaining water, and just like that, you've got a finished roll of paper. And that brings us to our final paradigm, a symphony of assembly. We can call it component integration. In this case, the final product isn't transformed from a single material. No, it's the sum of many different, complex parts, all made separately and then brought together at the very end. And the perfect example of this? A pair of headphones.
So if you want to understand how headphones work, you have to look at their heart, the driver. That's the tiny speaker that actually makes the sound. Here's how it works. An electrical signal from your music goes into the voice coil, turning it into a little electromagnet. That coil then moves back and forth in the field of the permanent magnet, pushing and pulling on a super thin diaphragm at incredible speeds. And those vibrations, that's what creates the sound waves you hear as music.
What's really fascinating, though, is that while those tiny drivers are being made, all the other parts of the headphones are being made at the same time using totally different methods. You've got the plastic parts being made with injection molding, the circuit boards being assembled by robots, the ear pads being cut and stitched. It's all happening in parallel.
And after all those different components are finally put together, the job still isn't over, not even close. Every single pair gets put on a test rig to make sure its audio quality matches up to a perfect standard. All the buttons and features get tested, and then a few units from every batch are literally tested until they break, dropped, twisted, you name it, just to make sure the design is tough enough for the real world. So, after taking a look at all these totally different ways of making things, we can kind of step back and see the bigger picture. We really do get a whole new perspective on the engineered world that's all around us.
The truth is, there isn't just one way to make things. You can go from melting sand with brute force to layering atoms with microscopic precision, from taking apart wood fibers and putting them back together to conducting a whole symphony of separate parts coming together. Our world is built on this incredibly diverse and, honestly, brilliant foundation of manufacturing ingenuity. And that really brings us to a final thought. After seeing all the hidden complexity that goes into these things, what everyday object are you going to pick up today and just see in a completely new light? Thanks so much for joining me.